This episode is being recorded on Christmas morning, 2014. Glad tidings to all whom these words reach. This is my gift to you. From us here in Middle Georgia to everyone around the world, we wish you joy. Break out the appropriate beverage, sit back, relax, and enjoy this great episode. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a mini-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 2, A History of the Atom. Episode 5.1, Supplemental. We three chemists of the Enlightenment are. In this supplemental episode, I would like to tell the stories of three very different men, all of whom I mentioned in the root episode, and the single discovery each man made. This discovery, oxygen, has a very tangled history, one of some scientific intrigue, and one that is illustrative of how difficult it can be to assign credit for work done in different places by individuals who are communicating with each other. However, I would also like to talk about the lives of the three men in more than the passing way, as they speak to a tumultuous time in Europe and the promise of a new place and way of doing things. Before we head down this path, however, I would like to acknowledge that the lives of these three men are well chronicled, along with a number of others in the history of science and in chemistry. There is a tendency, I think, to look at figures such as these and think that they are representative of all the work and research of a new phenomena, and that would be a mistake. Their work, as we have seen, is built on the work of those who have gone before, and even when that work or its interpretation has been wrong, it's still really important. Moreover, there are many names of investigators whose contributions were more minor or passing that are ignored, but that nevertheless added to the conversation. These lesser lights, as they might be called by some, added pieces to the steady accumulation of knowledge. Men and women such as Stephen Hales, William Brownwig, Marie Lavoisier, and numerous others made discoveries, recorded observations, and invented apparatus that made progress possible, and without whom the work of these three men might not have happened. Another observation that can be made is that almost all of these figures came from either the growing middle class of professionals, such as doctors, lawyers, and apothecaries, or from the nobility of their respective countries. This is a result of the increased stability and prosperity of the era that we call the Enlightenment, that I discussed in the root episode. Only Priestley, and later Dalton, seem to have risen up from humbler origins. However, it would be inaccurate to think that it was only this group that contributed to answering the questions we will be covering here. Just as much of the knowledge and experience they built on had come from the artisans, medicinal workers, and closet alchemists, so too would these same people contribute to the investigations done by the researchers of the day. For example, without the observations of the smiths and metal workers, the weight gain problem of the phlogiston hypothesis might have gone unnoticed for a lot longer than it did. Finally, as I've done my research for these episodes and other topics, I've found great variances to what writers call people doing the work. If we go back to ancient times, we find the term natural philosopher being used, and that certainly continued up through and even beyond the period of the 18th century. In France, where much of our story will take place, the term savant came into use during the 17th century and was used to describe those figures who were thought to have given their lives and energies wholly to the pursuit of knowledge, particularly knowledge outside the traditional considerations of philosophy and theology. Finally, we have the term scientist, which was also coming to the fore to describe those individuals who followed the rigorous methods of investigation required by the essays of Francis Bacon from sometime in the early 1600s. While some historians approve the use of this term, others, such as Ken Alder in his book The Measure of All Things, suggest that both the term science and scientist should only be applied to those investigations and investigators who seek to quantify and account for the error that always crops up in observation and research. If one adopts this criterion, science as a formal activity must wait until the development of statistical tools in the 1820s and 30s. I'm going to try to stay out of that controversy by referring to these individuals in accordance to the work that they actually did. I'm going to refer to them as researchers, experimenters, chemists, physicists, and in one case, minister. And that's where I think I'd like to start. The first and last man we'll talk about is Joseph Priestley. Born in 1733 in western Yorkshire near the town of Leeds, Priestley's parents were what was then called of a dissenting faith. That meant they were Presbyterians who didn't agree with the structure and theology of the Church of England. This entry into a world of nonconformity would have a strong impact on Priestley throughout his life. Precocious as a child, he was able to recite verbatim the answer to his faith's catechism at age 4. He was tabbed by his family to enter the ministry, and he undertook a course of study that led in that direction. By his teens, he had learned Latin, Greek, and Hebrew, and had been introduced to natural philosophy. By the way, as a side note, it's stories like Priestley's that make me feel like I was a slacker wasting my youth by running around the forests of Southern Oregon as a Boy Scout. Well, not really, but I think you get my point. Sometime around his 16th year, Priestley had a crisis moment that changed the course of his life. Coming down with some ailment, Priestley became convinced that he was going to die. His faith had taught that to be saved, one had to have some sort of conversion experience, and he hadn't had one. This called all of his theological beliefs into question and led him to reject the Calvinism of Presbyterians and move towards the theology of Unitarianism. For a time, he also gave up thoughts of ministry as well, training instead for a career in trade. And that led him to learn most of the languages of Europe, along with Arabic and Aramaic. During this time, he also continued his study of natural philosophy and began to think about how children were educated in Britain. At the age of 19, however, he returned to the pursuit of ministry work, and by age 22, he finished his ministry training and began pastoring congregations, initially in Suffolk and then in Chester. It was during this time that he began teaching in local academies to supplement his salary, and it was this work that led him to Warrington and the academy there. Over the 12 years of this ministry work, he wrote on history, theology, but most importantly, he composed a grammar book that was well received. He was an educational reformer who believed that the education of all people was a moral imperative, and thus he advocated for the admission to institutions of learning, both women and those of lower socioeconomic standing. His work in developing curriculum and other educational materials eventually led him to be awarded a Doctor of Law degree from the University of Edinburgh, and his books and timelines on history were used as widely as Cambridge, Yale, and Brown. The second figure in our story is that of Carl Wilhelm Shell. Born in 1742 in Pomerania, which is now part of Germany, but it was governed by Sweden at the time, Shell came from middle-class roots. His father was a merchant and brewer from a respectable family, and Shell, like so many others from this class of people, began his life working towards a profession, in this case, pharmacy. At age 14, in 1757, he began his apprenticeship in Gothenburg. For the next 8 years, he received the practical training in working with and mixing chemical and herbal preparations that would serve him in good stead as he pursued his chemical investigations. It was also during this time that Shell began his chemical experiments and became familiar with the phlogiston hypothesis that would shape and mold his thinking for the rest of his life. In 1767, he moved to Stockholm to work as a pharmacist and became acquainted with the cream of the Swedish scientific community. He began his investigations of various acids, as well as started to think about what air was and how phlogiston was related to it. 3 years later, in 1770, Shell moved to the biggest pharmaceutical laboratory in Sweden in Uppsala, and he made connections with the chemistry faculty at the university there and began his researches in earnest. Our third and final figure is Antoine Lavoisier. Born the year after Shell in 1743, Lavoisier was the son of a wealthy attorney working in the Paris Parlement. Beginning college at age 11, he studied to be a lawyer, but his heart was never really in it. He was more fascinated by the natural sciences, to which he was introduced through the lectures given at the Jardin du Roi. These lectures were given by one Professor Bourdelin, who expounded on all things Aristotelian, but did no experimentation or demonstration. This was left to the assistant, Guillaume François Roule, an enthusiastic apothecary who often became so animated during his demonstrations that he stripped down to shirt sleeves while presenting to the crowd, something of a scandal for a gentleman at the time. More importantly, Roule's demonstrations frequently contradicted Bourdelin's lectures and thus instilled in Lavoisier a mindset that experimentation was superior to untested theory. Following his admittance to the Paris bar, Lavoisier continued his work in science, establishing his credentials as a first-class researcher on mineral survey work in the region of Alsace and Lorraine, and in developing better lighting systems for the streets of Paris. It was for this latter work that he received a gold medal from the King of France and secured his election to the most prestigious scientific organization at the time, the French Academy of Sciences, at age 26. Shortly after this, he did the water transmutation research I discussed in the root episode. Also, he purchased a membership to a tax collecting firm that moved him into political circles. The revenue from this business venture would allow him to fund his chemical researches, but would also lead to his untimely death. On a more positive note, it also facilitated his introduction to the daughter of one of the firm's other partners. Her name was Marie. Only 13 at the time, Marie would wed Antoine within the year. Brilliant in her own right, she quickly became his associate. Possessing gifts in language and art, she translated scientific papers, created diagrams of apparatus, kept notebooks of the laboratory's work, and acted as an assistant in almost all of Lavoisier's research. Now established and settled, Lavoisier began his research into pneumatic chemistry in 1772, beginning with a thorough review of Black's work on fixed air. He was able to show that this gas was the same as what was produced when metals had been calcinated were restored through heating them with charcoal. This course of experiments moved Lavoisier in a direction that had already been taken by both Priestley and Shell. Now that we've introduced the three principles, let's take a brief look at their work. The earliest research was done by Shell, though he would be the last to publish his findings. Working in Uppsala, Shell was determined to understand phlogiston, and so turned to working with acids and their reactions with metals. He knew that such reactions always produce gases, and he was familiar with the work of Rutherford that indicated that air was a mixture of two of these gases. What Shell knew was that combustion led to a reduction in the volume of common air, and that the unbreathable air that was left behind, what Rutherford had called phlogistated air, was less dense than the common air had been. He came up with a hypothesis that said the phlogiston released by the combusted material had combined with some part of the common air, and that had been released as heat, which was weightless. As we said previously, he called this component fire air, and he wanted to isolate it. To do this, he understood that trying to work with combustion was difficult to control and almost impossible to measure. However, his work with acids had shown him a better path. During his research in 1770, he had reacted acetic acid with saltpeter that had been heated for a long time and observed a red vapor produced. His idea was that the vapor was a phlogistated gas, and he set out to work with it. Shell knew that nitric acid, when reacted with a metal, would act on the metal in the same way as heating the metal in common air would, what we now call oxidation. So he reasoned that the nitric acid must be absorbing the phlogiston from the metal the way the air was thought to when the metal was heated. If heat was fire air plus phlogiston, he figured that contacting the heat with nitric acid would draw off the phlogiston and leave behind the fire air alone. When he set up a reaction that would do this, he found that he could fill a balloon with a gas that would cause a candle to burn very brightly. When this gas was mixed with unbreathable air, it made the air breathable again. This meant that the isolation had been successful. Now, since Scheele was a devoted adherent to the phlogiston hypothesis, his picture of what was really going on was seriously inaccurate. But he had isolated a new substance as fire air for the first time in 1770. Unfortunately, he wouldn't submit his work for publication until 1775, and it wouldn't actually be published until 2 years after that in 1777. In England, Priestley began to become interested in natural philosophy around 1761. First as more of a hobbyist, Priestley would be drawn more and more deeply into scientific investigation in both electricity and chemistry, especially after moving back to Leeds in 1767. Modeling himself after the practical American he so admired, Ben Franklin, Priestley used the convenience of living next door to a brewery to investigate the workings of Black's fixed air. Incidentally, it is during this time that he developed a reliable method of dissolving fixed air in water, thus creating a pleasant drink he called soda water. This work won him the prestigious Copley Medal from England's Royal Society and established him as a preeminent scientific figure. It, of course, is also the foundation of the multi-billion-dollar soda industry here in the United States and around the world. So the next time you enjoy a can or bottle of soda, take a moment to raise your glass to Joseph Priestley. Now, Priestley's work also attracted the attention of the Earl of Shelburne, who, upon recognizing Priestley's varied and prodigious talents, offered the minister the position of being his secretary. For the next 8 years, Priestley would serve in that role, and it's during this time that he would do his best work in chemistry. As we've already discussed Priestley's work in this area, I will briefly summarize. Like Shell, Priestley did research with a number of gas-producing reactions. Working with mercury in around 1774, he was able to produce a gas that also strongly supported combustion, which he called dephlogistated air. This work would be published in 1776. Shortly, however, after that initial discovery of dephlogistated air in 1774, but before he'd had much of a chance to investigate it fully, Priestley accompanied Shelburne on a trip to France. During this trip, Priestley was present at a dinner where he met Lavoisier. During the meal, Priestley engaged Lavoisier in a conversation about pneumatic chemistry, wherein he is said to have discussed his work with various gases with the French chemist, including his dephlogistated air. Now, just prior to this meeting, Lavoisier had been doing experiments on calcination that showed, in the same fashion as Lomonosov had, that something from the air was combining with the metal to cause the change. What Lavoisier didn't know was whether the reaction was with all of the common air or just part of it. As one might imagine, coming right at this time, the conversation with Priestley stimulated Lavoisier's thinking, and following the dinner, he returned to his lab to isolate the gas and test it. It was as a result of these investigations that Lavoisier was able to isolate the gas from common air and show that it was what combined with metal during calcination. He established this discovery in a sealed letter to the French Academy in 1775, known as the Easter Memoir. In 1778, the full work was published widely, though no mention was made of the conversation with Priestley or the work they had discussed therein. By this time, Lavoisier had realized the flaws in the phlogiston hypothesis, and he recognized that the various gases that Black, Rutherford, Cavendish, Priestley, and others had discovered were actually different substances rather than phlogistated or dephlogistated common air. As Shell's work became available outside of Sweden, Lavoisier was able to incorporate these ideas into his picture as well. What he did was recognize that several of these gases, most notably oxygen, were elements and had properties that led to their specific interactions with other substances. No phlogiston was needed to explain what was happening, and in the spirit of Occam, Lavoisier eliminated the idea from his thinking and explanations. All of this led to a protracted and occasionally acrimonious dispute on two fronts between Lavoisier and Priestley. The first was over the phlogiston hypothesis. Priestley tenaciously clung to phlogiston, as did a number of others in England. It would be 2 decades before the scientific community would reach a consensus that would coalesce around the role of oxygen in combustion. This claim would be first championed by Lavoisier, of course, and then by a circle of associates and colleagues he had gathered around him in France. The second point of the debate was over claims of primacy of who had actually discovered oxygen in the first place. Historians of chemistry have established that it was Shell who first isolated the gas, but it is clear that he didn't have any idea of its true nature. Committed to the phlogiston hypothesis, Shell didn't see that it was a separate gas that he had found, but instead thought that it was the same gas that he was always working with that just lacked a non-existent substance. Nevertheless, it seems that Priestley had read some of Shell's work and that those readings may have influenced his thinking significantly enough that there is some question as to whether he would have been able to isolate the gas on his own without that work. Of course, as we've discussed, Priestley isolated the gas before Lavoisier, and the dinner conversation certainly spurred Lavoisier to move his research in a specific direction. However, like Shell, Priestley had failed to grasp the fundamental nature of what he had discovered. In part, this is due to the fact that Priestley missed the key piece of the puzzle, which was investigating calcination. By focusing on this and seeing the other work of pneumatic chemistry in light of the bigger picture, it was Lavoisier as the one who was able to bring all of that work into focus and develop an accurate model of what was really going on. So who discovered oxygen? I think it can be said that all three did within the context of a broad scientific atmosphere, and while each man benefited from the work of the man before him, or perhaps more accurately it would be said, the nearly simultaneous work of all of the men around each person, they didn't always recognize what they had done. Only Lavoisier was able to see the results for what they really were. This story, therefore, highlights two things, I think. The first is the importance of the framework of knowledge one is working in. Kuhn called this a scientific paradigm, and it was vitally important to how each man interpreted their results. By working from within the phlogiston hypothesis, Shell, Priestley, and even Cavendish missed the true meaning of what they were doing. Only by rejecting this paradigm and adopting a new view of combustion was Lavoisier able to understand oxygen as something new. The second, however, is the recognition that it is very rare for a scientist to create something out of whole cloth. Lavoisier can probably be credited with discovering oxygen, that is, the community reached by the broad chemical community. But it is a lot less likely that he would have done so without the work of Black, Shell, and Priestley, or indeed Lomonosov. In this sense, Lavoisier was as much a synthesizer of the work as anything. There are those who say that the French chemist actually did little of his own original research, but I think that misses the point. Lavoisier's original work wasn't in creating new chemical reactions or in isolating new gases and acids, as many of him before had done, but it was an understanding that the pathways to knowledge involved both precision of measurement and a rejection of the phlogiston hypothesis. To end this supplement, let's take a look at the fates of each of these men. Isaac Asimov would refer to Carl Scheele as Hard Luck Shell. This is due to his discovering so many things but receiving so little credit for his work. In addition to being the first to isolate oxygen, though we didn't know that's what it was, Shell also discovers chloride gas, barium, manganese, molybdenum, and tungsten, as well as a number of acidic compounds and lime. He received almost no credit for these discoveries due to being burdened with trying to explain his researches using a faulty model and by not having a good definition of an element to work with. As was the case with Priestley and Lavoisier, Shell was not only a gifted individual, but he worked really hard on his craft with a tremendous attention to detail. Unfortunately, it was his work that likely eventually led to his early death. His nearly constant contact with toxic substances, most notably mercury, slowly destroyed his kidneys, and he died at the surprisingly young age of 43 in 1786. While Lavoisier would live longer, he too met an early end. His involvement in the tax collecting firm, so important to funding his chemical research, would ensnare him in the worst excesses of the French Revolution. In 1791, the tax collection firm was more or less put out of business due to reforms in the French tax structure brought about by the National Assembly. In 1792, he was forced to resign his post as the overseer of gunpowder production and had to move his home and laboratory. As the revolution became more anti-intellectual, the French Academy of Sciences was repressed along with a number of other learned societies. And once Robespierre got a hold of the levers of power, the reign of terror was on. In 1793, Lavoisier was accused of treason by a jealous colleague whose election to the Academy he had once blocked, and in 1794, he was led to the guillotine. In response to this untimely death, mathematician and physicist Joseph Louis Lagrange wrote, "It took them only an instant to cut off his head, and 100 years might not suffice to reproduce its like." In England, Priestley's life also took a negative turn, though not quite as fatal. As a lifelong dissenter who had turned to Unitarianism, Priestley was viewed with suspicion by a number of those in power, and his support of the American Revolution did not make him a lot of friends. However, it was his willingness to positively engage in the dialogue of the French Revolution that finally got him into real trouble. The British had already gone through their revolution and regicide and had no interest in going down that road again. In 1791, due to several writings critical of the Church of England and attempts to loosen the grip over religion it possessed, the people of Birmingham, where Priestley had settled, had decided they'd kind of had enough. Priestley and a number of other dissenters in the area had planned to celebrate the anniversary of the storming of the Bastille 2 years earlier. However, this provocation was not going to be allowed to pass, and in a series of riots in Birmingham, Priestley's home and laboratory were destroyed, and he and his family were forced to flee into hiding. For 3 years, he had to keep a low profile, and in 1794, he finally immigrated to the United States and settled in Pennsylvania, where he founded the First Unitarian Church of Pennsylvania and continued his scientific work. For the next 10 years, he participated in scientific dialogue as best he could, given the remoteness of America from the center of the chemical world in Europe and his stubborn adherence to the phlogiston model. Nevertheless, he was a powerful advocate for scientific research in the new and growing United States. As I close, I should note that what I've presented here is just a sketch of the lives of these three men. You do very, very well to go out and read more deeply about them. This is especially true in the case of Priestley, whose writings on topics from theology to politics were always insightful and provocative. The great scientist and lifelong minister died on February 6, 1804, on the eve of Dalton's publication of an idea that would remake humanity's view of the world in which they lived. Given his many contributions to knowledge, it is fitting that I leave the final words of this supplement to him, in the form of the epitaph written on his gravestone. "Return unto thy rest, O my soul, for the Lord hath dealt bountifully with thee. I will lay me down in peace and sleep, till I awake in the morning of the resurrection." Until next time, full sails on your journey.